let's do the lecture nobody asked for. This lecture is on the hyperreals. Now, I've been doing some previous lectures on the theoretical bases of various number systems we use. Integers, rational numbers, which is ratios of integers, and also the reals, which is the completion of the integers, where we see that the completion of the rationals. The rational numbers are incomplete in that there are sequences, or Cauchy sequences, that look like they're going to converge on a value, and then they miss. So we think there's a lot of holes in the rational numbers. In fact, there's more holes than numbers. So the rational numbers, I want to do the construction of them again because it gives us a good starting point how to construct the hyperreals. The hyperreals are a special extension beyond the real numbers, which includes infinitesimals, numbers much closer to 0 than any real number, which basically lets you do things like the calculus in the style of Newton and Leibniz, using what they called fluxions, or infinitesimals, but ones that actually have a firm mathematical basis, not like the ones that were eliminated by the criticisms of Bishop Berkeley. And let's go ahead and start. So the rationals we can define two ways. We'll start with a set Q, which is not the rationals, and it is all the pairs A, B, such that A and B are integers, and B is greater than 0. And we normally write these pairs as numerator over denominator. That's the notational convention. Now there's two ways to promote these numbers, these symbols, into the rationals. The first way is the way I showed in a previous lecture. And we'll just call this Q unique. It's all the A, B in Q such that either B equals 1 or the greatest common divisor of A and B is 1. I'm just special casing out the fraction 0, 1. So let's say A equals 0, 1 in this case, or the greatest common divisor is 1. It's basically saying we're not writing things redundantly. We're not writing 1/2 as 2/4, and we're not writing 3 as 9/3. We write it as 3/1. So what we've done is we've taken the redundancy that what we consider a fraction has multiple representations as different pairs, and we've taken a favored pair to represent it. The other way we can do this, instead of picking a unique representative, is to go to equivalence classes. So we'll call this Q equivalence, and it's defined as Q modulo the equivalence relation. So this means, this compact notation means we take Q equivalence. It's defined as all the sets of AB, write that A1, B1, A2, B2, ... So it's a set of items contained in Q. And the equivalence relation is A1, B1 is the same fraction as A2, B2, or what clear denominator is A1, B2 equals A2, B1. So every single way to write the same fraction is in this set. So this one we took a distinguished representative, this one we take all equivalences, ram them into a set, and that's called an equivalence relation construction. This construction is the one preferred by mathematicians, that we think of rationals as equivalence classes of pairs of integers, not as always just distinguished pairs of integers. So one of these equivalence classes would be 1/2, 2/4, 3/6, and so on. The hyperreals are constructed from the reals. The idea is the reals are complete, but let's just do some things acting to see if we can extend them again. So the way we do that is called a product. So we'll start with the hyperreals, and this is not them yet, so we'll just call it this, and it's defined as the set of all sequences, where this is x1, x2, ... and these are infinite sequences, where xi is in R. So this is a very large and unruly set. And we can define the field operations on it, which is addition, multiplication, division, subtraction, things like that, by saying x1, x2, x3 times y1, y2, y3 is just the coordinate-wise pair, x1, y1, x2, y2, x3, y3. Now, in classic times, they might have written this as a free sum, that the notation in mathematics used to not use vector notation, especially for infinite vectors. This is an arbitrarily long vector. So they would often write this as sum I, xi, and then maybe some p to the I, where p is just a symbol, so we can tell them apart. But they never would actually take the sum. This was just a system they manipulated formally. I like the vector notation much better. This set is awful. It has the one thing we really don't want for our field of numbers. It's called a zero divisor. So if A is the number 0, 1, 0, 1, and this keeps repeating zeros and ones in that order, and B is the number 1, 0, 1, 0, and it keeps repeating 1, 0 in that order, well then we have A doesn't equal 0, B doesn't equal 0, yet A times B equals 0, which means it's very problematic how to divide by B since it can multiply into 0. This is a failure of a field called zero divisors, and this means that this is a horrible set to do arithmetic on. It is just, even though its components are real numbers, it behaves horribly. So we're going to do something that's very common in mathematics. We're going to fix this. And we're going to fix this by adding a very interesting control structure or accounting system called an ultra filter. Some of the more scary mathematical objects are really just accounting or rule systems to prevent other things from going wrong. So a filter is a very abstract term, and it's defined as such that it's a set of subsets. In our case, it will be a set of subsets of the natural numbers starting at 1. So we'll just call this n plus. It's defined as 1, 2, 3, and it's exactly the indices of these numbers. That's why we're using these natural numbers. Now, a filter, in our case, for our application, it's a very general concept. We're going to be using a particular one, a particular ultra filter, is a subset of the power set of these positive natural numbers. So this 2 to the n notation is a notation for power set. It means the set of all subsets of the natural numbers, including the empty set. So a filter is a subset of all the subsets, or it's basically a selection of subsets. Abstractly, filter equals large. It's the picking of what are all the large subsets of the natural numbers. For instance, we can do a principal filter. We can say F3 is defined as S contained in the positive natural numbers, such that 3 is in S. This obeys the filter law. Every set is either large or small, so it's a complete filter or an ultra filter, that basically everything that's not listed, every set that isn't in the filter, its complement is in the filter. So if S is not in F, then n minus S is in F, the complement's in the filter. So basically, any way you split the natural numbers into two sets, one of the sets is large and one of the sets is small by the filter accounting. And it says basically you're large if and only if the number 3 is in you. So that gives us our filter, and this also gives us our hyperreals. The hyperreals are just defined as this set. Hyperreals are written as R, star R, and it's defined as this crazy set or product set R modulo an appropriate ultra filter on the positive natural numbers. If, for instance, if we use F3, we get that the only thing that matters is position 3. The way we use the filter is we say two hyperreal sequences are equivalent if they are identical on some large set. Now, for F3, the large sets are all the sets containing position 3. So these two numbers are equal because, these two numbers are not equal because they are not equal on this large set, which is the set 3. They're also not equal on larger sets. The filters are containment. Large sets, anything containing a large set is also large by the filter axioms. But this is called a principal filter, so we really only need to examine this special set 3. So this number is equal to 0 under our equivalence relationship because it matches 0 on a large set, position 3. This number is not in the equivalence class of 0. So A times B is 0 because A was already in the equivalence class of 0. A was already a representation of 0. Not obviously the best representation of 0, but it's already 0. So we don't have 0 divisors because due to the filter axioms, any two numbers multiplied, if the only way their product can be equivalent to 0 is it must be equal to 0 on some large set, which means one of these two is already equal to 0 on some large set. Because the ultra-filter axioms, if it's the largest possible filter, you essentially have A intersect B is in the filter if and only if A and B are both in the filter. So this is what powers the thing. So the only way we could have a bunch of 0 positions in the product, on a large set in the product, one of them must have already had 0 positions in some other large set, or possibly the same large set before the product, at least one of them. So we don't have the 0 divisors, which is the whole purpose of the filter technology. At this point, we have brought ourselves absolutely nothing. That we have not fixed our problem because R3, defined as R prime modulo F3, well, that's isomorphic to just the reals. Because all it's doing is tracking what happens in position 3 and saying everything else doesn't matter. That's all this equivalence class is saying, that two sequences are the same if and only if they agree in position 3, which means the other stuff's all ignored. Again, these two are considered isomorphic also. So what do we do to get something useful out of this construction? We introduce, from advanced set theory, a new filter called a non-principal ultrafilter. So it's a filter not driven by the element membership. Now, the non-principal ultrafilter, the large sets are all the sets that are cofinite. So cofinite means a set F contained in N plus is cofinite if F equals N plus minus A1, A2, AK for some A's. So it's basically a cofinite set is all of the natural numbers minus at most a finite number of points. So those are large sets. They're almost all the points of N. That's not an ultrafilter. It is, for instance, an ultrafilter would have to decide whether A or B is equivalent to 0. Because you can think of this as an indicator function of a set. A is talking about the set where it has ones, B is talking about the set where it has ones. Together, their union is the entire natural numbers, and our ultrafilter property is if we have A union B equals the positive natural numbers and A intersect B is empty, then one of them is large and the other is not. That is the property of the ultrafilter on the natural numbers. So the ultrafilter, which is bigger than the filter that's just the cofinite sets, makes these decisions. It writes down, and that's why I call it an accounting procedure, which one of these is non-zero in a large number of positions. One of them is, but it's an arbitrary decision which one. How we make those arbitrary decisions, we use set theory. We basically assume that somebody has built for us an ultrafilter with all decisions already made. How is it possible to make all decisions for every pair of sets decide which one's large? Well, it turns out that involves the axiom of choice. So it's non-constructive. There exists set theories where the axiom of choice isn't true, which means these ultrafilters don't exist. And there exists set theories where the axiom of choice is assumed true. And in those set theories, the ultrafilter does exist. Any filter, like our cofinite filter, can be extended into an ultrafilter by an induction style argument in those set theories. Now, we commonly use set theories with the axiom of choice, and actually a slightly weaker relative to the axiom of choice, a Boolean algebra axiom will do, but it's still something about infinity you have to assume. So we're assuming something like the axiom of choice to say we believe there is a non-principal ultrafilter, that any filter can be extended to an ultrafilter, so we take the filter of all cofinite sets and extend it. Once we do that, we get the actual hyperreals. Now, it is the case that any prefix of these x's is a small set. The large sets include all right tails of this sequence. So two numbers that agree from one point on are in the same equivalence class. I can't say everything's in the same equivalence class, but some of them are obvious. So basically, if these stopped repeating and just went all zeros both, we can ignore any prefix and say that's a finite prefix, therefore they're the same number. Now, what we wanted from all of this is a new number. And our new number is epsilon. And it's the equivalence class, but I'm going to leave out the class. Well, I'll just say this is form equivalence class. And it's 1, 1/2, 1/3, 1/4, ... So epsilon is the sequence, the equivalence class generated by this sequence, where the ith position is 1 over I. The field of the hyperreals has an order operator, and it says that two numbers are equal if they agree on some large set. That was what we said was identity, or equivalence. That's the equivalence relation that came in with our non-principal cofinite ultrafilter. We can also do order. We can say a number is less than another number if, for some large set, it's always less. Epsilon is less than any standard real. A standard real, or at least a member of that equivalence class, is just the same number everywhere. So we could put a 100th here, 100th here, and at some point, this fraction dips below our constant, and from that point on, epsilon is below that real. So for every non-zero real number, epsilon is smaller than it. Or sorry, every positive real number, so this isn't true for zero or negative real numbers, but for every positive real number, something like epsilon basically lets us do our calculus just like Newton and Leibniz did it. They don't have to take limits. They can define the derivative as f of x plus epsilon minus f of x over epsilon. They can literally compute the derivative that way without having to introduce a limit as epsilon goes to 0. We can actually stick in a specific epsilon that is known to be small enough to make that work. Now, the one thing I've left out is a big, big feature of the hyperreals, which is usually we have to set up quite a large logical framework about formulas to get this important theorem called the transfer principle. And that lets us prove theorems in the hyperreals and lift them back to the reals, which is basically, instead of doing limits, we calculate in this weird ring symbolically, and theorems we prove here become theorems in the real numbers by this sophisticated tool called the transfer principle. But that's the hyperreals. It's an equivalence class of a product or sequence of reals. Under the equivalence, two hyperreals represent the same number if they completely agree on a set of positions that forms a large subset of the natural numbers. Large being defined by our counting procedure called the non-principal ultrafilter, which is, in this case, we seeded it from the cofinite sets. One of the consequences is we have this order relation that a hyperreal is less than another hyperreal if its real components are less than it on a large set of indices. And this, because finite prefixes of a thing are small sets, their complements are large by the ultrafilter property. So if there's an epsilon, a number like epsilon that's less than any real number at a certain point. What point it is depends on what real number, or any positive real number. Then this has to be less than every positive real. And that gives us something that behaves just like the fluxions or infinitesimals from the early calculus. For this sort of calculus, we don't need limits. We directly calculate just like Leibniz and Newton did. However, it's on a number system that is thought to be sound, and the infinitesimal is not a bolt-on that we argue in and out. Now, obviously, this is getting a little weird. I did say by the time you get to the hyperreals, most people think you've gone pretty nuts. But this is the hyperreals. They're actually a very late invention by Abraham Robinson in 1966. So they've not been with us for that long in the history of mathematics. And they settle a lot of open questions on the style and content of the calculus, only quite a lot later. Thank you very much for your time.